we just realized that the naive algorithm to compute GCD, scales as the minimum of the two numbers, and as the minimum of the two numbers becomes large, the time runtime also linearly increases, and that is kind of inefficient, right? And that's not surprising because really that was a naive algorithm, right? Now, smartness in this case comes from an observation by Euclid. This theorem we learn in school. You can try proving this, that Euclid observed that GCD of A and B is the same as GCD of A minus B and B. In fact, we can prove this by using mathematical formulas related to modulo, or you can also prove this graphically. Very interesting. GCD of A and B is GCD of A minus B and B. In fact, I highly recommend you to try this, and share your proof. This is a nice exercise in mathematics, right? But for now, let's just take a few examples because, like I said, our focus is here algorithms. Let's take this mathematics to be correct and build algorithms based that, right? So basically, a few examples help. So for example, if I had GCD of 15 and 10, well, that's same as GCD of 15 minus 10, which is 5, which is 5 and 10. And that's indeed 5, right? So 45, 25, very useful. In fact, you can apply this, quite to get GCDs quite fast. 45, 25, the same as 20, 25, because 45 minus 25, which is same as 5 and 20. So I take 25 minus 20 and 5 and 20, that is indeed 5, right? Really good. So 420, 280, you can get it for 140 and so on, right? So 96, 72, for example, is same as 24 and 72. So I took 96 minus 72, which is 24, and 72, which itself is 24. So really, you can see it's quite fast. But the real magic happens when we use this smartly. What do I mean by this, right? Think about, let's say I have two numbers A and B, which are such that A minus B is also more than B. What does that mean? So when I do GCD of A and B, well, I will say that's same as GCD of A minus B and B. I can go and say, well, look, A minus B is more than B. So I can go further and say, then GCD of A and B should be GCD of A minus 2B and B. If it turns out that A minus 2B is still more than B, I can go further and say this was GCD of A minus 3B more than B, 3B and B. Well, what this means is that, in fact, we can go on and find that Q, all right, find that Q where for the first time A minus QB becomes less than B. Because in that case, we can get there because GCD of A, B is basically GCD of A minus QB. Q is presumably more than 1, right? So it could be 2, 3, 4, whatever, right? So what that means is that I can come down from this computation not to A minus B, A minus 2B, A minus 3B, and so on. In fact, I can very quickly drop down from A, B to, let's say, A minus, for example, 10B. We'll talk about this later. A minus 20B, right? So we can very quickly keep coming down. Now at this point, remember, B has become B has become more than A minus QB. So which means that the roles reverse, but the same process can continue until one of the two becomes zero. Now, really, really cool when we see this working. Let's take an example to convince ourselves. Let's say we had GCD of 1900 and 400. Now, in this case, we know that GCD of AB is A minus B and B. So yes, I definitely know that it's 1500, 400. But 1500 is still more than 400. So I say, okay, that's basically 1100, 400. That's equal to 700, 400, and that's equal to 300 and 400. Notice this is the first time where the 300 has become smaller than 400. Basically, whatever came from 1900 has become now smaller. If you think about it, I could have come directly from here to here. I didn't need to go through all these steps. So you can already see that the number of computations is being reduced dramatically. Next, 400, 300, which is same as 300, 400. Well, again, I can apply the same principle. It's the same as 100, 300, which is the same as 100, 0, and which is in fact 100, right? So if you think about it, you can just go 1900, 400 to 400, 300 to 100, 0, and that is 100, right? So really, we can just cut through the entire computation very, very, very fast. And in fact, do this much, much, much faster than what we were doing in the naive algorithms. The challenge, however, is how do I find this Q? What is that smallest Q such that A minus QB is less than B? Think about it. This is where it gets very interesting. In fact, A minus QB is the remainder when A is divided by B. To see this, you can argue that, look, if let's say A is QB plus R, remember R is less than B, all I need to do is to get to this R, which is nothing much but the remainder when A is divided by B. So, long story short, again, I urge you to think carefully about this. Very, very interesting what's going on. There's a nice graphical, way to look at it, as well as algebraic way to look at it. Try to convince yourself meaningfully that, look, I really don't need to find what is A minus, what is this Q. In fact, all I need to do is to find A modulo B. And that gets me to the algorithm, which we are going to do next, which is basically, while B is not equal to 0, remember I'm assuming that B is the smaller one, so A is more than B. I just find the remainder. I initialize A to B and B to remainder. Now remember, remainder is going to be smaller than B by definition. That's the way mathematics is, right? So, remainder is always smaller than B, and hence I'll always make sure that the smaller one goes in the, in the second, as a second argument. And I run this loop in a while loop while this B is not equal to 0. So basically my algorithm will push this B towards 0, and whatever remains in A is my GCD, because GCD between A and 0 is indeed A. So that's the whole idea of this algorithm. Let's code this up first. So I define, so maybe I'll just put a small text over here, GCD smart, say Euclids. So I put in a function, I just call it, say, def GCD smart A and B. So these are two arguments, two integers. Let me just put a couple of comments. So A, B are positive integers, and assume A is greater than B. So I always make sure that the first argument is a larger one. And all I do is to say while B is not equal to, say, 0, while B is not equal to 0, well, basically find the modulo, find the remainder. So I just say remainder is A modulo B. I assign A to B. So B is remember A is the larger one, so A will take on the value of B, and B will take on the value of the remainder, which has to be by definition smaller than B, right? And thereafter I just go and say return, say, A. Now again, be careful with the indentations. This return statement has to be a part of the function, and the while loop, and be away from the while loop, right? So when I, let's say, run this, seems okay. I can start using this already. So if I do GCD of, let's say, say 96 and say 72, okay, I have to be calling the right function. So GCD smart, let's say GCD smart here, right? So when I do this, it is indeed 24. Let's take one more example. Let's say 999 and say maybe 666, just an example here. Well, that is 333, right? But let's say if I were to try two prime numbers, 1009 and say 340, just trying something, the GCDV has to be 1, right? So indeed it looks correct, because this is 1 because 1009 is prime number, right? So nothing else divides it basically except 1 and itself, right? And hence the GCD is 1. Now, just before I wrap this up, let me just talk a little bit about why this condition B not equal to 0. This could be a little bit confusing. What exactly do I mean by, the loop breaking when B becomes exactly equal to 0? Well, think the way to understand this is kind of here. So for example, if I have GCD 100 and 300, 300, 100, the next step would be GCD 100 and 0, because the modulo is 0, right? In this case, we know clearly the GCD is 100. In fact, the same answer comes from here, right? So whenever I have two numbers which have become multiples of each other, the GCD is a smaller one. And that's where I'll end up with, because remember, the remainder will become 0, and the smaller one, which is smaller previously, will become A, and hence the GCD will be that. Think about it. Very, very interesting. This is the reason we can keep repeating the while loop while the remainder is not 0, right? Remember, while loop runs while the condition is correct, right? So now with this function setup, we are going to come back and analyze how long it takes to run this. What is the efficiency gains we are gaining with this? In fact, they're quite impressive. But we'll see this in the next video. I hope you found this interesting. If you want to understand algorithms in a lively, fun, hands-on manner, look at our website www.ybyte.in and search for the algorithms and Olympia track in YByte. Take care, forever enjoy coding.